Hello everybody. So I found this math question on my school's math textbook, and it's way harder and more interesting than the other one, so let's do it. Pat has 30 meters of fencing to enclose 3 identical, let's highlight that because it seems important, stalls behind the barn as shown. What dimensions will produce a maximum area for each stall, and what is the maximum area for each stall? Okay, so let's see. The stalls are essentially 3 squares with one exception. Now the exception is that this side is given. So this is the big trap that I fell into when I was first doing this question. Usually when you have a question like this, 30 meters of fencing are this perimeter and you're trying to get the maximum area, you just distribute the fencing evenly. Because let's say you have the number 26 and like you only have numbers that add to 26 and you're trying to multiply to get the most numbers, it'll always be the middle. Like the closest pair that gives you the best result, the biggest result. And I'll just show you here. Let's say 26. Okay, 13 times 13. Probably don't need a calculator, but it's 169. Let's go up 1 and down 1, so the sum stays the same. As you can see, it becomes 1 less. If we go again, just to make sure, becomes 4 less. So yeah, I don't know how to prove it, but I just know. Also, I know intuitively. But anyways, when I first did this question, I thought it was just like this. So how can you split 30 meters into 4 squares? So each side would be there would be 1, 2, 3, 4, 5, 6, 7 sides. So I thought each side was just going to be this because it follows this principle. But no, this is wrong because these are 3 normal squares. If they were, this would be exactly correct, but they aren't. This side is, you can think of it as it freely filled out without having to use up any of the fencing, right? So if you think about it, you can make this width longer for more value than the height. Because for the height, if you make the height, and this is a rectangle, so it can't be like a trapezoid or something. So the width and the height stay the same across each other. If you make the width longer, then both widths get longer. So you're essentially doubling that effect. But in this situation, because this side is given for free, if you make the width, height. If you make the width longer, you only have to make one side longer because this one is given. So we already know that to maximize the area just out of logic, that the width is going to have to be more than the height. And this is something we can use to check our answers. So a lot of the times, logically, you can deduce a question down to some limitations, but you have to use precision in numbers, manipulation of numbers to get a precise result. So let's map out the equations using the symbols. So A, what dimensions? Well, what are we're given, and because these are identical, this is, let's say the width is x, the height is y. These y's are all the same, so this is y, and same with x, because the question said the situation is identical stalls. So we can say that 3x plus 4y is equals to 30. Then we can't really map out another equation that has two variables, so only height and width, that would only have two variables, so we can solve it as a system of linear equation with two unknowns. But we can do it with three variables. We know that area is 3xy because the squeeze squares. But at first, if you're really rigid in the head, you can look at this and say, there's no way to find x. Like, what are you even trying to find here? Like, if you had something like this, you can find x and y. But first of all, that's not really like, I don't understand what you would be finding there. You'd just be finding for a certain area and perimeter. You can look at this and say we have three unknown variables, and the rigid mind would think, oh, well, you can't get anything from this. There's three. But that's what vertex form and factored form of quadratic equation stuff is all about, right? You get a form of an equation like this. Let's say vertex form. This is the standard way to denote vertex form. Okay, so you don't know the output of fx, which is essentially y. You don't know y. You usually know a, you know h, and you know k. But then you can tell so many things about this relation with two unknowns, because you can essentially do a glorified trial and error to find the vertex, as long as you know what all the numbers in the relation mean, instead of just looking at the numbers. Of course, a number itself doesn't have any value at all. For example, if I said the number 4, or gave you the equation 3x plus 7 equals 23, of course, this equation has no meaning whatsoever, but it's the way the school gives you it, which is why students think math has no meaning whatsoever. Numbers themselves have zero meaning. But when humans psychologically give meaning to numbers, then they become meaningful based on the meaning that the humans gave to the numbers. So let's say this was an equation of everything, like the universe. Let's say it was just this. You inputted the amount of consciousness into the universe, and this is the years that the universe would live. Now, all of a sudden, basically the same equation becomes extremely meaningful. I'm sure if this equation was true, there's going to be many, many millions of minds, billions of minds thinking about this and making deductions on this. So anyways, back to the question. What I mean was that even if you have two unknowns, as long as you know the meanings of the variables, it can still basically give you all the information you usually need to know. Okay, so we can already isolate x here. I mean, let's isolate x because we can divide easier. So x would be equals to minus 4 divided by 3y plus 10. And now, because we know what x is, we can write that in the y form of x on this. And then we turn this into vertex form. So you could do all this algebra, but basically the fun part of the question is over already. So if you want to know the answer, x is 5 and y is 3.75 to maximize the area. And then, of course, you can just plug in the numbers to find the area. Thank you.